Okay, so in this video clip, we're going to take a look at some interesting source code for R, running R in Google Colab. And very specifically, we're going to take a look at the functions available in the fOptions package that you can pull down, load into the Google Colab environment, execute in R code. In particular here, we're going to take a look at the Black Scholes model, its valuation, the Greeks, and then implied volatility. And this code is coming from Diethelm Wuertz, based on Espen Haug design. And I'm going to leave the link there to these resources just here, and you can follow that below the video clip. So first of all, just to take note, the fOptions package, if you want to go into, well, very specifically, if you want to take a look at the fOptions package, here it is, and then source code, and I'm going to look at the plain vanilla options. So embedded in there, we're going to have code for some basic distributions. We're going to have code for running Black Scholes model, the distributions here, the cumulative normal distribution, the cumulative bivariate normal distribution. And again, this is coming, the reference here is Espen Haug, the complete guide to option formulas. And then the generalized Black Scholes option functions. And this again is following a template that was previously set up by Espen Haug. So if we take a look here, it's the generalized Black Scholes option pricing model for futures. There's some distributions we're going to set out, and then implied volatility and the Greeks. So this is the code that we're going to use here, and I'm going to demonstrate how you would implement the code. So the code, while provided here, the next step is, well, how do you run and execute the code, and how best to make use of the code. So if you load that in and implement here, you make the code functional, or you make the code execute, but numerically we need to run the code. Okay, so to observe what's going on here, to run our code in Google Colab, you just need this magic cell so we can execute. And then that entire library, or that relating to the plain vanilla options.r, that file I'm going to load in. So the one we just were taking a look at, I will load that in its entirety, right? And that's executed without any issues. And so we have the cumulative normal distribution, we have the cumulative bivariate normal distribution. Again, these are being implemented by Diethelm Wuertz based on Espen Haug. And then we run the generalized Black Scholes model using the template set out by Espen Haug, the complete guide to option pricing formulas. Okay, so embedded in here, then we have the different Greeks, and the formulas are presented there. The Black model 1976 for estimating options and futures. And then there's this Middleton Schwartz option pricing formula for pricing options on commodities. We'll run that, execute, and then we have some implied volatility. So all that's executed here, and we're going to load in, again, following, I'll leave the link here to the code and so on, to Espen Haug. But we're going to load in then actual numbers based on numbers explained in Espen Haug's textbook. Maybe I should just go into the textbook just to point it out. So there's the option pricing formula that Espen Haug has published, and we're looking really here at chapter 1, some numerical examples he runs through in chapter 1 of his textbook, chapter 1 and 2, and we're going to estimate some values here. So we're going to look at if the stock price was 60, the exercise 65, 3 months to expiry, risk-free rate of 8%, cost of carry 0.08. So B here is equal to the risk-free rate minus the dividend yield, and then sigma of 30%. So if we run that code using these parameter inputs, we get this output, right? And the price there is 213. And then I run the same GBS option function again, but take values that I typically use in videos that I use. So the stock price 100, exercise 100, time period 1 year, risk-free rate 5%, B or R negative Q is equal to 5, so dividend is 0, and sigma equal to 0.2. And the value we get out is that 1045. And we know that to be correct. Okay, so this function seems to be working properly, no issues. Now I've other code from Python where we can run the same values using the same parameter inputs, just to do a check here. So Python is what's native in Google Colab. We don't have to do anything other than just execute that snippet. And you can see here for the call option, we're getting 1045.058, which tallies with the results that we have here, right? So that's looking good. It's looking promising. There's an example there provided in the Espen Haug textbook. How do you deal with cash dividends? So I'll just execute that. You might take a look at the actual textbook. There's an example if you run on stock indices. And again, this is a very specific example in section 1.2.3. And you can see the value we are obtaining here. Now, options on futures, typically we would have a futures price and we have 19. So the futures price is equal to S. We're setting X equal to 19. The time period is 3/4 of a year. Risk-free rate is 10%, and B. So we're setting Q equal to the risk-free rate. Right, so this is an approach that Espen Haug adopted for estimating the option price or the options on a futures price, where the futures price is the underlying, right? And the value we're getting there is 170, right? So this is one way of estimating using the Black Scholes approach by setting this F equal to S, the spot price, and by setting B equal to 0, so Q is equal to the risk-free rate, the Black Scholes model defaults to a Black 1976 model, right? So that's one approach. So we have a GBS option model again here. This is a currency example, we run that, and again, you can see the value we obtain, and you can compare that against the actual value set out. Now, interestingly here, we can use the GBS Greeks and selection delta. So we have a call option, stock price 105, X is 100, time period is equal to 6 months, risk-free rate equal to 10%, B equal to 0. So dividend is the same as the risk-free rate, and sigma is 0.36. And if we execute that, we get the delta of the option. Okay, so there's a few more examples you can run down there where you specifically set out gamma, vega, theta, and rho. And keep in mind, this is all coming from our source code, right? All the estimations are being based on the source code that we extracted here from the fOptions package. Okay, now if we go down to the Greeks for a moment. So I'm going to run the generalized Black Scholes formula. I'm going to output here all of this. So if we say GBS characteristics, load in, is it a call or put? So CRP, and then the values we have for the option. These are standard values that I typically use. Then we should get 1045 for the value of the option, and we have a delta, theta, vega, rho, and gamma. And I've previously estimated C++ code to estimate the Greeks. And again, I follow, this get the density function, bool. This is based on code from Fabrice Rouaves, made some small changes here. So to include a different yield. And if we load in these parameters, which mirror the parameters we had before, execute that code. Remember, that loads into the content folder. And if we take a look here in the content folder, that's the function we've loaded in there, right? And then to execute it, we run a bash command in the line below, keeping in mind that the name of the file here is it's mainstat. Okay, so this is the C++ code. And then to execute that C++ code, we use a bash command, and then it outputs, and we have the A out here as well, right? So that's gobbledygook, but it's Black Scholes is 1045. Now we can compare that against the R snippet of code that we had. So if we place that to one side here and go back, we can compare directly our results here against the results we had previously estimated here. So using this command from the fOptions R package, where the option is a call, it's a European option, the stock price is 100, exercise 100, time period equal to 1 year, risk-free rate 5%, dividend 0, and sigma equal to 20%. You can see that the values we obtained here are the same as the values we have here. So the delta, for instance, is 0.63, 0.63, the gamma 0.018, 0.018, the Vega 3752, Vega 3752, the rows 5323, 5323, and that's our estimate. We can also get the theta, right, which corresponds to what we have here, and then there's a daily theta as well. Okay, so the code that we have used previously for running C++ for Greeks is consistent with the output. And again, it's a further check that the estimation is being run properly. Okay, so there is a Diethelm-Wuertz option formula. We can run that. And so for pricing options, there are some Greeks there. I won't necessarily go into that. I might take, however, a little bit of a deeper dive here on the Black 76 options. Again, that's based out of the fOptions R package. And I've run that snippet of code, and I get this output for the value of the option. And I take a set of values again from a previous example I used before. So if F, the futures price is 127, X 110, time period 1 year, risk-free rate 10%, and sigma is 8% using the Black 1976 model, the value of the option is 1558. And then if I run some C code, right, C++ code with the same parameter inputs, and then output that main CPP, you can see we're getting 1558. So the values here again tally, and that's useful. That as a check in terms of are the results for fOptions consistent with an example I took from the Hull textbook, John C. Hull, Option Futures and Other Derivatives, right? So this numerical example I worked out, we know that the value is 1558, and the fOptions package is also producing the same value. So I'm comfortable that this code is working fine. There was also a function set in the fOptions for implied volatility. And basically what we're doing here is we're reversing, we have one unknown in the Black Scholes environment, and that is the volatility. But we do know what the option price is. We do know if it's a call or put. We know the stock price. We know the exercise. We know the time or maturity of the option, the risk-free rate, the cost of carry. What we don't know is sigma. And typically, we actually have these values and we can extract directly from the market or the option contract. What we typically don't know is the implied volatility, which we're going to call sigma. We know from our example when we had sigma equal to 20% and these other parameters, we're getting a value of 1045. So now we've reversed engineered that and we're pulling out 1045 using a unit root, getting the root here. And again, we can compare that directly against an example we had done before using C++. So I'm going to run main CPP. So the name of the file here is main CPP. That overwrites the existing file. And then if I put in these parameter inputs and say, look, stock price is 100, exercise 100, risk-free rate is 5%, time period or maturity 1 year, no dividend, and we're going to start at a low ball guess of basically a value very close to 0 or a high ball guess of 700% for the option, and then this bisection technique will keep estimating until we converge to some minimal level of error. So that the price here is 1045.06 as before. If we run that and then output, execute the main file here, we get a value of 0.2. So these parameters are consistent with the parameters we had obtained here before, 1045, it's call, stock price. And when we compare like against like, here, maybe we'll post this to one side here. Okay, so when we compare the values we have here against the C++ execution, we're getting the same result, right? 0.2 or 0.199, which is basically the same thing. Okay, so that's an introduction to fOptions, some of the functionality that's available. There's plenty more in there, and you probably would like to run it in an environment that you could share. Google Colab is really good at that. If you want to find the source code, I recommend coming here, rdrr.io, and you can go in there and look for different snippets, different functions that are available. Baron Alice Whaley, roll, Gesk, Whaley, so on. They're all standard models for pricing. American options, there's Monte Carlo techniques, there's Heston, Nandy, Garch, Fit. They're all really good models, standard models. The Gesk, as far as I know, the Heston model isn't available in the Espen Haug textbook. And there's also, I should point out as well, R metrics. So if you're a little bit at sea with the discussion around these options, a good source here is R metrics. If you go into R metrics for a moment, there's a free textbook. Maybe I should leave the link to that. But basic R for finance, this is a free textbook if I remember correctly. So let's double click on that. We can download, comes up as a PDF file, and then there's case studies for option valuation. So if you're brand new to option valuation, some explanation around the Black Scholes option pricing model, some formulas that could be useful in trying to understand what's going on, the D1, D2, estimating P, some of the logic here for the generalized Black Scholes approach, which is really coming from Espen Haug, and how we can use B to pivot B in order that we revert to the Black Scholes or the Black model or Garman Colehagen model for currencies, and then some explanation around the functions and how you write functions in R, so R implementation. And there's quite a bit in there, just quite a few examples, most of which we touched on as we went through the Google Colab. The Greeks are explained a little bit, some of the formulas that could be quite useful. The rho, theta, delta, gamma, and reference to John C. Hall. And again, that's probably theta, and so on, right? So I think that could be a valuable resource to people running through the fOptions package, and I think it enhances the methodologies that are available, and is worth considering. So have a look through this textbook. I think it's a very useful textbook, and worth exploring. Okay, the next section then, section 8 here, is the case studies for portfolio design. That's something that worth exploring in its own right. Okay, I'm going to leave this video clip here and hope that it was useful.